In this video, we're going to go over the KutaSoftware Infinite Pre-Calculus free worksheet, Motion Along a Line. Now in numbers 1 and 2, it says a particle moves along a horizontal line. Its position function is s of t for t greater than or equal to 0. And t usually represents time in this case. For each problem, find the velocity v of t. The graph of s of t is provided, and we're to use the blank graph to sketch v of t. Now, since the particle is moving along a horizontal line, and the position function is given to us, s of t, v of t, that velocity function is going to be the derivative of our position function. Again, that's because the particle is moving along a horizontal line. So we're going to find the derivative of s of t, because the derivative of that function is our velocity function. So we'll use the power rule, sum rule, and constant rule for finding that derivative. First of all, we know the constant will go to 0. So when writing v of t, using the power rule, the exponent of 2 will get multiplied to 1, because 1 is the coefficient of t, and then we'll decrease that exponent of 2 by 1. So we'll have 2t to the first, which is simply 2t. So now that we've taken care of the first term, we're going to move on to the second term. So if t is raised to the first power, when we bring that 1 down, we're multiplying it by 25. Or we can think of it as multiplying by a negative 25. So that will become minus 25, and then t to the first, if we subtract 1 from that, that will be t to the 0, which is simply 1. And 25 times 1, and then our constant is 0. So our velocity function, v of t, is 2t minus 25. And again, the velocity is the derivative of the position function. So now what we're going to do is graph this. The y-intercept is negative 25, and the slope is 2 over 1. But because my interval is so large, I'm just going to use a t-table. So let's plug in another value, let's say 12. So v of 12 equals 2 times 12 minus 25. 2 times 12 is 24, and 24 minus 25 is equal to negative 1. So when we're at 12, in respect to time, we're at negative 1. So I'll now draw a line connecting those points since this is a linear equation. And that's our answer in number 1. But quickly, before we move on, I want to point out that remember, the derivative is equivalent to 0 at a min or max, so at a point of extrema. And you can see here, the derivative is 0 a little past 12, and when we're looking at a little past 12 for t in respect to the position, that is a minimum. It's decreasing until that point, so our derivative is negative up until that point, and then once it hits that point, it crosses the x-axis, therefore the derivative is 0, and then it begins to increase. So then the derivative is positive. Let's move on to number 2. Number 2, we're going to have a cubic function, but remember, the derivative of the position, because the particle is moving along a horizontal line, is velocity. So we're finding the derivative of f of t, and that's equal to v of t. So here are our terms. Starting with t cubed, we're going to multiply the exponent of 3 to the coefficient, which is 1. So that will be 3 times t to the 3 minus 1, which is 2. Then I'm going to be subtracting 2 times 16, or we can think of this as adding a negative. And when we multiply 2 to a negative, we will get a negative, so we can think of that as subtracting the positive. So 2 times 16 is 32, so we're going to be subtracting 32t to the 2 minus 1, which is 1, or 32t. And then lastly, for 64t, that is an exponent of 1, so we'll bring down that exponent and multiply it to the coefficient. So we'll be adding 64, and that will get multiplied to t to the 1 minus 1, which is t to the 0, or simply 1. So our velocity function is 3t squared minus 32t plus 64. So our velocity is going to be a quadratic. Now, feel free to use a t-table to help you plot each of the points. However, I'm going to make it a little bit easier. Graph this on a graphing calculator and then plug in points from there. So the derivative of my function is 3t squared, but I'll use the variable x, so 3x squared minus 32t, so 32 times x, and then plus 64. So let's go ahead and graph our x-intercepts. Our x-intercepts are at 2.667, so 2 2/3, and then at 8, so 2 2/3, and at 8, we're crossing over that x-axis. So our derivative at those points are 0. And if you look back at our position function at 2 2/3, we have a maximum, and at 8, we have a minimum. Up until that maximum, our position is increasing, so I know that our derivative is going to be positive. So I'll go ahead and plot that y-intercept where t is equal to 0, and that occurs at 64 for v of t. So 0, 64 is another point on our velocity graph. Finding the minimum, that is 5 1/3 and negative 21 1/3. So 5 1/3, negative 21 1/3. And then let's go ahead and give us another point. Let's look at 14 in the x, or t equal to 14. There we go. I just quickly adjusted the scale so that it's a little bit easier to compare a graph. So here again, we had our y-intercept, x-intercept, minimum of the derivative, x-intercept, and now we're looking at where t is 14, which is 204 for v of t. So now I'll go ahead and connect those points to form my parabola. So now let's look at the different parts of the graph. From t equals 0 up until our maximum, our function is increasing. And from those same t values, our velocity is positive. Then, if we were to look at from the maximum to the minimum for position, the function is decreasing. And you can see that for our velocity, we have negative velocity. And then lastly, our function begins to increase again, and that is where the velocity is once again positive. Let's continue on to that second page. So again, we have a particle that's moving along a horizontal line with a position function s of t for t greater than or equal to 0. For each problem, we're finding the velocity, but this time it's going to be at a given value for t. So we're going to find the instantaneous rate of change. So we're going to find the velocity, which we know that the velocity is the derivative of the position function. But then once we find that velocity, we're going to plug in our given value of t. So we'll go through the same steps. We'll find the derivative, graph that, but then we're going to plug in 5, in the case of number 3, for our t value within our derivative to find the velocity at that given value of t. So let's first find the derivative. The derivative, v of t, using the sum rule, we're going to look at each of these terms. In that first term, we're using the power rule, multiplying our exponent of 2 to the coefficient of 1, which will give us 2, and that will get multiplied to t to the 2 minus 1, which is t to the first, or simply t. Then we're going to be subtracting, because we can either think of subtracting 4t as that, or as adding a negative. But when we're multiplying by that exponent, with the exponent being positive, 1 times negative 4 is negative 4, so as opposed to adding the negative, let's just keep subtracting the positive. So we'll have 1 times 4, which is 4, so subtracting 4, and then t to the 1 becomes t to the 0, which is 1, and 4 times 1 is 1. So we have 2t minus 4, and then the derivative of a constant is 0. So our derivative, v of t, is 2t minus 4. So let's go ahead and graph that. Well, we can use our y-intercept of negative 4, so 0, negative 4 is 1 point on our velocity graph. And then the next point we can use, well, let's just go ahead and plug in 5 and solve. So plugging in 5 for v of t, we get v of 5, which is 2 times 5 minus 4, and 2 times 5 minus 4 is 10 minus 4, which gives us a positive 6. So v of 5 is equal to 6. So our velocity, otherwise known as our speed, at time t is 6. So graphing 5, 6, we now have 2 points for our linear equation and can sketch that velocity graph. So v of 5 equals 6 means that when t is equivalent to 5, our velocity is 6. Now we'll continue on to the last problem on this worksheet. In order to find the velocity, we need to find the derivative of s of t, because that is equal to the velocity. So looking at our first term, we're going to have 3 times 1, which is 3, and that will get multiplied by t to the 3 minus 1, which is t squared. Then we'll be subtracting 2 times 20, which is 40, and then we'll be multiplying that by t to the 2 minus 1, which is t to the first, or simply t. And then for our last term, we're going to be adding, if that's an exponent of 1, 1 times 100 is 100, and t to the 1 minus 1 is 0. And t to the 0 is equal to 1, and 1 times 100 is 100. So our velocity function, v of t, is 3t squared minus 40t plus 100. So let's go ahead and graph that using our graphing calculator to help us plot those points. So again, we have 3t squared, or 3x squared, minus 40t minus 40x plus 100. And I'm going to adjust my scale because I'm going from negative 400 to positive 400 in the y. So our y-intercept, when t is 0, v of t is 100. So I'll go ahead and start by plotting that point. Then at t equals to 3 1/3, or 3.333, we're at 0. So 3 1/3, we're at 0 for the velocity function. Our minimum occurs at the point 6 2/3, negative 33 1/3. So I'll plot that. 6 2/3, negative 33 1/3. Our next intercept occurs at 10, 0, or our next t-intercept, in this case, is 10, 0. And then I'll graph one more point, let's say 14. V of 14 is 128. So 14 and then 128. Now I'll go ahead, draw my parabola connecting my points. So now we have the velocity function sketched. However, it asks for the velocity when t is equal to 4. So we're going to plug 4 in for t. So v of 4 equals 3 times 4 squared minus 40 times 4 plus 100. So that's 3 times 4 squared, which is 3 times 16, minus 40 times 4, which is minus 160, and then we're adding that to 100. 3 times 16 is 48, so we have 48 minus 160 plus 100. 48 minus 160 plus 100 is equal to a negative 12. So v of 4 equals negative 12. And let's double check using our graph. We'll go to v of 4, and it appears to be negative 12 on our graph as well. And that's the final solution on this worksheet. However, before moving on, let's quickly go over the graphs one more time. Our function is increasing from 0 until our maximum, which you can see for that the derivative is positive. Then it's decreasing from the maximum to the minimum. So from when the derivative equals 0 to the next time the derivative equals 0, our function is negative because that position function is decreasing. And then lastly, our position function is increasing after that minimum and on. So you can see on our velocity function, we are again positive. So keep that in mind and just get familiar with how the velocity function or how the derivative function relates to the position function or the original function, because that will be helpful later on. And if you haven't done so already, don't forget to like, subscribe, and share.